Hey there, it's Shannon Mapchick-Myers, and today we're starting section 7.2. We'll be focusing on inverse transforms, and then I'll be making another video that goes over transforms of derivatives. So in the next two subsections, we will be checking out the inverse of a Laplace transform, capital F at S, the Laplace transform of derivatives, F prime at T, F double prime at T, and how both the Laplace transform and the inverse Laplace transform are used to solve some ordinary differential equations. All right, so 7.2.1, inverse transforms. If capital F at S denotes the Laplace transform of a function f at t, so that means that L at f at t is equal to capital F at S. We say that lowercase f at t is the inverse Laplace transform of capital F at S. Oops. And lowercase f at t is equal to L inverse at capital F at S. So we did a couple, these three examples last time. We got that L at 2 was 2 over S. And so our inverse transform, therefore, will be L inverse at 2 over S is equal to 2. Good? All right, and then similarly, L at T was 1 over S squared. And so L inverse at 1 over S squared is equal to T. And then when we did the Laplace transform of cosine at 3t, we got S over quantity S squared plus 9. And so that inverse Laplace transform of S over quantity S squared plus 9. Unfortunately, in the application of the Laplace transform, we are not able to determine an unknown function f at t directly. We are able to solve for the Laplace transform, capital F at S of lowercase f at t. From this result, we find f by computing f at t is equal to the inverse Laplace transform at capital F at S. All right, so here we go. Some inverse transforms that will be handy to know. 1 is equal to the inverse Laplace transform of 1 over S. T to the n is equal to the inverse Laplace transform of n factorial over S to the n plus 1. And that's for n equal 1, 2, 3, ... E raised to the AT would equal to the inverse Laplace transform of 1 over s minus a sine at kt would be the inverse Laplace transform of k over s squared plus k squared cosine at kt, the inverse Laplace transform of s over s squared plus k squared, the hyperbolic sine at kt would equal to that inverse transform at k over s squared minus k squared. And then the hyperbolic cosine of k at t, or at kt, would be the inverse Laplace transform at s over s squared minus k squared. Cool, cool? All right, so now let's take a look at the next little bit here. In evaluating inverse transforms, a function s doesn't exactly match the form of a Laplace transform, capital F at s, given in a table. You may need to multiply and divide by an appropriate constant to fix it up, just like we do with integration. And so, first example, let's use the appropriate algebra and theorem 7.2.1, which was this here, to find the given Laplace transform. So this one, so the formula we have that looks like the first problem where we have s raised to a power needs the n factorial. So if n plus 1 is equal to 4, n will be equal to 3. And so what we're lacking here for the official transform is the 3 factorial in the numerator. So this would be equivalent to 1 over 3 factorial times that inverse Laplace transform of 3 factorial over s to the 4th. Now it's going to fit our formula, and so we'll get 1 over 3 factorial times t to the 4th, which of course is what? T to the 4th over 6. Cool, cool? And just to kind of match up what's what, this whole thing right here had this output. Groovy? All right, so next up here, this is equivalent to the inverse Laplace transform of 1 over s squared plus 4 squared. Well, that one kind of looks like sine at kt, right? Because we can adjust by a constant. So what I need to do is I need to multiply by 4 here and by 1/4 on the outside. And then I will get 1/4 times sine at 4t. And we're all done. Aren't these fun? All right, so it turns out that L inverse is a linear transform. So the inverse Laplace transform is also a linear transform. So for constants alpha and beta, the inverse Laplace transform of alpha times capital F at S plus beta times capital G at S is equal to alpha times the inverse transform of capital F at S plus beta times that inverse transform of G at S, where capital F and capital G are the transforms of some functions lowercase f and g. This equation extends to any finite linear combination of Laplace transforms. All right, so now example 2, we want to use algebra and that groovy theorem to find the Laplace transform. So here we go. This would be equivalent to, so using linearity and recognizing that I need a 1 over s, I'm going to take factor out of 4, and then we're going to have the inverse Laplace transform of 1 over s. Now, here, notice that we have, the next one we have 6 over s to the 5th. And remember, this one here, the t to the n factorial over s to the n plus 1. Well, our s, whoops, sorry, our s is raised to the 5th power. 5th power, so n plus 1 is 5. So n, therefore, would be 4. And 6 is equal to 3 factorial, right? So if we multiply a 4 times 3 factorial, we would have our 4 factorial that we need. Sorry, this isn't an equals. This would be a plus. And so we'd also have to divide by 4 in order to balance it out. So we're going to have 4 times 3 factorial over s to the 5th, and then minus the inverse transform of 1 over, we need an s minus something, so we'll write it as s minus negative 8. Now remember right here, this is 4 factorial, so we're set up for our transformation. So we will now get 4 times 1, applying that first transform, plus 1/4 times t to the 4th. This is applying our second transform. And then minus e to the negative 8t. And that's applying this last one, this last transform. And so at the end of the day, we will get 4 plus t to the 4th over 4 minus e to the negative 8t. Cool, cool? All right. Now let's take a look at this guy. So what I'm looking at here is I have an s squared, and then I'm adding a 1. And so the closest thing to that in here, and I don't have an s in the numerator, is again going to be that sign at kt. So let's take a look at what we have going on. So would you agree that this would be equivalent to that inverse Laplace transform of, if I divided everything by 4 in the fraction, each part, I would have this going on. Cool, cool? All right. Now, 1/4 from that bottom portion is 1/2 squared. So I need a 1/2 in the numerator. And so I'm going to multiply by 1/2 outside of the inverse transform and by 2 inside to get my 1/2. That in turn is going to give us 1/2, and then I'll write it nicer before I finish it off, times that inverse Laplace transform of 1/2 over s squared plus 1/2 squared, because that's what a quarter is. And that will give me 1/2 times sine at 1/2 t. So this here has an output of this. All right, moving right along. Now we've got something where we have to be a little bit more creative. So here, again, we've got an s squared plus something. So let's check it out. We're going to split this up. You can't split the denominator up, but you can split the numerator up. So we'll end up with this sum of Laplace transforms. You'll have s over, I'm going to write this as s squared plus the square root of 2 squared. That's set up for the cosine, the result of cosine root 2t, plus the inverse Laplace transform of 1 over s squared plus root 2 squared. Now that is almost set up to be that sine output. So what I'll need to do is times it by root 2, which means I have to divide by root 2 as well. So now let's see what shakes out. This is going to be cosine at root 2t plus 1 over root 2 times sine at root 2t. And this is how they shape up. This whole transform is this here. And then this one is this portion here. All right, so now this one's going to take a little more work. We're going to have to do some partial fraction decomposition to write this in a desired format. So when we factor the denominator, we're going to have, we need to have a negative 20 as a product. And then when we combine like terms, we get a positive 1. So if we have s plus 5 and then s minus 4 will be golden. That's going to equal to a over s plus 5 plus some b, because they're linear factors, over s minus 4. So I just need to get common denominators. So I'll omit the denominators as I am getting a common denominator now. Now notice I have an s term, so I need to have a 0s plus 1. And then this will be a times s minus 4a plus b times s, bs, plus 5 times b. And this is where we're matching coefficients, so we'll end up with a plus b times s plus negative 4a plus 5b, and that would be equated to that constant term. So here we're just equating coefficients. So a plus b is 0, and negative 4a plus 5b is 1. A will be equal to negative b. Substituting that in over here, we'll have negative 4 times negative b plus 5b equals 1. 9b is 1, so b is 1/9. Well, if b is 1/9, then a, coming back over here, will be negative 1/9. So here we go. Coming back here, we can say this is equal to that inverse transform of a was negative 1/9, right? So negative 1/9, and a is over s plus 5 plus positive 1/9 over s minus 4. Now, these are in the terms where we'll get that exponential out. So I'm going to utilize our linearity property and then match the format. We'll almost be there. All right, so this will be negative 1/9 times e to the negative 5t plus 1/9 times e to the 4t. And we're all good to go. All right, one last example here. Let me box this up and highlight out the transforms. So this whole transform yields this result. This whole transform yields this result. All right. So now, example 3. Find the given Laplace transform by finding the Laplace transform of the indicated function f. So we have to leave this one till later, and we have to find what the transform, Laplace transform is for f at t. Well, plugging in for f at t, we have a times t minus sine times a, or sine at a times t. And using linearity, we'll have a times L, the Laplace transform of t, and then minus the Laplace transform for sine at a times t. All right, well, this will be a times, remember t is 1 over s squared, a over s squared plus a squared. So that's going to give us a over s squared minus a over s squared plus a squared. Getting a common denominator, we'll have a times s squared plus a squared minus a times s squared all over s squared times s squared plus a squared. Notice that the a(s) squareds will zero out and we'll have a cubed over s squared times s squared plus a squared. Now, notice that's not exactly like what's inside the L inverse, right? So, if we're now taking a look at L inverse at 1 over s squared times s squared plus a squared. Well, we know what we'll get if we inverse this one here, right? We'll get at minus sine at at. So if we multiply this one by a cubed and then we divide by a cubed, we will get 1 over a cubed times a times t, what we started with, right? Minus sine at a times t. Groovy? I hope you have a wonderful morning, afternoon, or evening. And if you like what I'm doing, hey, let's hit that like button and subscribe. Bye.